Hi, this is Michael. This is my final project for DSC478. I have my notebook here, and I just thought I'd go through a few of these cells and explain what's going on here. They've been pre-run, so I'm not going to run anything. I'm just going to discuss a little bit what you see here. So obviously this is a boilerplate stuff, and load the libraries that we want, a little bit of formatting going on here. Load the data set. There was something I was doing for PCA later that it would lose its references to the indexes that were provided in the data set, so I had to peel off the CRN that was with this so that I could later match the auto-generated one. I didn't end up needing that, but rather than take it out, I just left it. So that's what that's about. Pretty normal here. There's the CRN, so that we can relate that to an auto-generated index. One thing I wanted to do is, because I was interested in the severity, and we're defining severity as severe as if there was either a major injury or a fatality. And there were a couple of values of 8 and 9 for the max severity, which meant they were unknown. There may have been an injury, but they don't know how severe it was, or they just didn't even know if there was an injury at all. Because I thought that would mess up the results, I decided to take those records out. So that was about 31,139 rows, but out of 170,000, that didn't seem to be too terrible. I did spend some time looking through several of the fields. Again, we started with about 189, I believe, and there were some that were redundant where we could get, like, for example, here there's a bicycle count versus is there a bicycle? Well, they both cover the same thing, bicycle, so I only needed one of the two. And also because we're predicting the severity, I wanted to take out anything that was related to injury, whether it's minor or major or fatality. So those were all removed. So that's what's happening here. So that eliminated quite a few features. Next, I went through to see if there were any missing values, and I just did it the quick and dirty way, just to show me all of them. So I went through each of these trues and proceeded to deal with them as I went along. So hour of the day I felt was important, so if we had any that were missing, which I had replaced with 99, I took it out because hour of the day was important, so I wanted to use that in the prediction, so I didn't want to leave any unknowns in there. So that was about 2% of the data was removed that way. With weather, I filled the NAs with the unknown, about 230 out one of them. There wasn't that many, so I decided to also take those out because I thought weather would be important. So then I looked again for any remaining missing values, which there were. There's this roadway surface type code, which were things like gravel or concrete or asphalt, and there were a lot of unknowns, a vast majority. So in that case, I just got rid of the entire column because unknown isn't going to be a predictor of anything. I found also with special jurisdiction, I think those are things like military bases and state parks, things like that, that most of them were unknown or didn't have a value, so I took that out as well. Traffic control devices, there weren't that many unknowns, but I thought it was important, so I deleted any records that had unknown for traffic control devices. Checking again for any missing values. There are a few more. It's interesting with these traffic detour indicator, there was a Y or an N or a U. I just assumed U to be unknown, so I just added those in there looking for those unknowns. So I wasn't really worried about detours, so I just assumed there wasn't any detours if it was unknown and just changed them to N. And it carries on in that fashion down here. So lane counts were weird, so we took the lane counts out. Speed limits, I took out any that were unknown. Next, did some visualizations of any of the categorical variables. This is explained down here, so I included my explanations down here of my results here. So anyway, So you can read through those. Then on to the predictions. I did a PCA first, and it starts after making dummy variables. Oh, I want to point out here that I wanted to do some correlation analysis. It's difficult with the high number of features, but what I did is that I did save that out. Hopefully this shows up in the video here. And spit it out in a spreadsheet. I was interested in our target variable and seeing if there was any correlation between our target variable and any of the other features. And I didn't find anything that was super strong, but there's some like detour and others that were, pointing to a weak positive correlation, pedestrian, those kind of things. So I wanted to take a further look at those. So I pulled those out here so that we could just see them a little bit more closely right within the code. All right. And another thing is I wanted to look for any other multicollinearity. I didn't do much with it. I spit this big long list out. It's in reverse order, so the high correlations are down here. I had thought about going through here and removing any of these that were high, but instead decided to just let PCA take care of that. So split into train and test. I did not do any standardization. I elected not to because most of these were either ones and zeros or a few things with counts, but those numbers were so low that I didn't. I decided it didn't need to be done. Okay, performed the PCA, did a goal of 95% variance retained. It still came up with 131 components, which is really high. But out of 384 or whatever it was, I guess that's only a third. So, boom. So this is just graphing it, showing it about here, somewhere 131. Did a regression here. I found this clue doing a Google search to make this run a little bit faster. Anyway, here's all the coefficients. I wanted to pull out that these four components are likely the most important based upon their coefficient. There's a table that shows all the different weights for each feature in each component. I did not go through these to see what was, belonging to what most likely. Like person count was probably in component 0, but I did not take the time to go through those. It's a big long list. So here we do the prediction. Just spit out a few results to see how they compared. Here's one where I got it wrong. It was actually a 1, but it predicted a 0. But the accuracy was at 97%. Great, right? Now, so okay, it got 92 of the yeses correct, but missed 705 of them, and incorrectly predicted no for 68 out of the total. So I wanted to go through and do some other regressions doing some different ways. So I want to do some feature selection instead of PCA. So I found this recursive feature elimination functionality that I tried. So I went through and I ran it. I picked that I wanted to retain 3 features. And this tells you which ones were selected. So here's the number of features. And then I didn't find a good way to do this. You essentially have to go through either these true or false, or look for the ones down in here to know which features to keep. So I went through the true false and found where all the trues corresponded to these 3 indexes. So based upon those indexes, I got the column names. So here they are. So then I created a set with those 3 columns, split it in the train and test, ran it through the regression, came up with these coefficients, showing like of those 3, bicycle was the most important. However, even though it had almost 97% accuracy, which we would get that even if we predicted 0 for everything, it did not correctly predict any yeses. It didn't incorrectly predict any no's. So I did it again with 10. So I got some more columns, and it only did slightly better with one correct yes. So it just for curiosity, I went for broke, and let's just do a regression with all the features intact. Let's not take any out. So I did that, still at 97% accuracy. Here's all the coefficients. I summarize them a little bit later. But as far as the confusion matrix, 103 correct yeses, which was better than the PCA by a few, and 80 incorrect no's, which was only slightly worse than the PCA. So then here's all those coefficients. But in the long run, the real issue is that there's so few data points that had severe that it's hard to predict out of this data set. So as far as the regression is concerned, this wasn't all that useful. But was useful maybe because I don't know that we would ever predict the severity of a car crash. First of all, you'd have to be able to predict that a crash is going to happen in the first place, and then all the elements that are involved. So I don't know that we can really predict one and then prevent it from happening. I think what's more helpful out of this analysis is to look at some of these distributions of these features, and see if there's any kind of pattern. Like here was interesting that obviously this first one is the city of Pittsburgh. So we find in cities there's more accidents than any place else. We find that there's no difference in the year. The month, winter is a little bit, so people need to be more careful in the winter. Hours of the day, this seems like their afternoon drive time. The day of the week, Friday, everybody wants to get out. And then some other things on here. So really, a lot of these things are all just behavioral, because it's like weather wasn't a factor, and road conditions weren't a factor, and there's lighting in here somewhere was like sunny day, so it wasn't a factor. So it seems to be that the biggest takeaway here that most of these incidents occurs in cities at lower speeds, at times of congestion. So that speaks to people changing the way they would drive to avoid accidents as opposed to anything else that we can really do. So, right, I've gone over 5, but thanks for listening. Thanks.